Today we're going to talk about mole conversions. This is going to be the backbone of our stoichiometry calculations, so we need to understand some things about it. The mole is the basic SI unit of quantity. This is 6.02 times 10 to the 23rd of anything you can think of. We got some useful mole conversions that we'll use in chemistry, some of which are as follows. If we're looking for particles or counted things, there are 6.02 times 10 to the 23rd of those in a mole. If we're looking at mass, 1 mole is going to equal a molar mass, or the mass of 6.02 times 10 to the 23rd of that particular particle. And then volume, if we're operating with a gas at STP, 22.4 liters of that gas will occupy 1 mole. And in that sense, we're talking about a gas at 273 kelvins and 1 atmosphere, or 101.3 kilopascals. In order to understand what to do with the mass conversions, you probably should understand molar mass. And really all that says is that if I were to add up the individual elements in a compound and add up the contribution of each one, that would tell me a formula mass. If we are to expand that up to a mole, we can use that same number and call it a molar mass. As it turns out, there are 6.02 times 10 to the 23rd atomic mass units in a gram, so it works out nice and easy for us in that sense. Mole conversions will also follow your basic dimensional analysis, and they're going to be in every meaningful stoic calculation that we do. So now we're going to just look at some quick examples of how to deal with these. So the first question went too far. First question we'll do deals with particles, and it's going to determine the number of oxygen atoms in 3.65 moles of oxygen gas. So we'll do this like a normal dimensional analysis problem. So we'll write down what we know, 3.65 moles of O2 gas. We know from what we said in the previous slide that in every 1 mole of O2, there are 6.02 times 10 to the 23rd O2 atoms, molecules. And since this wants to know about atoms, we need to do one more conversion. There are 2 moles of O in every 1 mole of O2 molecules. And so if we were to execute the calculations for this, we would get 6 times 6.02 times 10 to the 23rd, or approximately 7 times 6.02 times 10 to the 23rd, whatever it may be. But we'll execute this in simple mathematical format. 3.65 times 6.02 times 10 to the 23rd times 2. Another example has to do with mass. If we're wanting to know how many moles of iron chloride we would have to mass out to get 45.2 grams. We can do this in the same manner. We write down what we know. 45.2 grams of iron 2 chloride. We know that 1 mole of iron 2 chloride is going to be equal to the masses of iron and 2 chlorine atoms added together from the periodic table. 2 chlorines are 71, iron is 55.8, so that should be 126.8. And so if we execute the math in that system, that will tell us what the number of moles of iron 2 chloride I must weigh out. And that is going to be about 0.36 moles of iron 2 chloride. Last, we'll deal with our volume at standard temperature and pressure. We want to mix zinc metal with hydrochloric acid, and we'll produce hydrogen gas in a product. If I'm to trap that hydrogen gas in a balloon and find out that its volume is 1456 milliliters, then how many moles of hydrogen did I produce? Well, I'm going to go ahead on the fly here and make notice that this is 1.456 liters, and that's what I'm going to use as my known. I'm also going to realize that 1 mole of any gas at STP, in this case it's H2, is equivalent to 22.4 liters of H2. And so the number of moles of hydrogen gas that we produced is going to be found by executing the simple algebra, and it is 0.065 moles of hydrogen gas. Now, sometimes we have to do things that are just slightly more complicated than this. It's not always quite that easy. In this case, we want to find the mass of a certain volume of xenon gas. Now, there's no direct road between any of the three things we talked about, particles, mass, or volume. In order to move between them, you always must go to the mole first. So we're just going to add an extra step to the end of these. We'll treat it like we did a volume problem, 55.8 liters of xenon. We are knowing that at STP there are 22.4 liters of xenon in every 1 mole of xenon. And we can also tell from the periodic table that xenon has a mass of 131.29 grams for every 1 mole of xenon. And we can run that through a calculator and get an answer. In the interest of time, I'm not going to do that. We could also find the iron atoms in 75 grams of iron 3 oxide. To do this, we still write down our known, 75 grams of iron 3 oxide. Refer back to your nomenclature and formula writing PowerPoint presentation if you don't remember or understand how I came up with Fe2O3. We're then going to apply the logic that 1 mole of Fe2O3 is worth a certain mass of Fe2O3, and that mass is going to be 159.6 grams. And then from looking at this formula here for Fe2O3, I can see that there are 2 moles of Fe for every 1 mole of Fe2O3. That still doesn't get me done. That tells me how many moles of iron atoms. This particular problem wants to know how many individual iron atoms, so we're also going to have to multiply by 6.02 times 10 to the 23rd per mole. If we were to execute all of those through the calculator, which you can do at your leisure, you can find out how many iron atoms are in iron 3 oxide. Last topic that we want to talk about in this presentation is percent composition by mass. Essentially, all this means is to take the mass of each piece and to split it out so that we can see what percentage of a total compound mass is from any given piece. Why is this important? This can be very useful in identifying compounds. Many compounds, due to the law of multiple proportions, have similar elements in them. There are many compounds of nitrogen and oxygen, but if you know the percent by mass, it's very easy to tell the difference between these compounds. So how do I do it? Well, this is one of the easier things that you'll do all year. The first thing we're going to do is find the molar or formula mass of a compound. That's simple, like we did with the iron 2 chloride, the iron 3 oxide. We just add them up. And then we're going to take each individual piece of that mass and divide it by the formula or molar mass, and then multiply by 100 so that we can see the actual percentage that we get. So here's an example of this. To find the percent composition of caffeine, first thing we're going to need is the molar mass of caffeine. So caffeine is made up of 8 carbon atoms and 10 hydrogen atoms and 4 nitrogen atoms and 2 oxygen atoms. All that together makes up caffeine, and that happens to be 194 grams. To find the percentage of each of these, we're just going to divide. I know that 8 times 12 of those grams come from carbon, and that much of it out of the 194 times 100 is going to tell me what percent carbon. That happens to be 49.4% carbon. Hydrogen makes up 10 times 1 of those grams out of 194. That happens to be 5.2% hydrogen. Nitrogen, 4 times 14 divided by the 194 times 100 is 28 9% of the total. And finally, the oxygen is 16 times 2 divided by 194. That comprises 16.5% of the total. Now you can go back and check these and add them up and make sure they add up to 100, but this is about 55 and this is about 45, so they should come close together just by visual estimation that we're going to be really close to 100. And that is the end of the subject matter for this presentation.